Hello, hello, hello. 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 Okay. Sorry about that. I'm eating. Hmm. That was a nervous gesture right there. What I just did just now. Sorry, not sorry. Okay. So for this lesson, this week, well, last week we covered most of linear regression, um, but I don't believe it was thorough enough. But this week we are going to cover the rest of the linear regression, and then we are going to talk about logistic regression after that. But that's gonna be a small thing because I still feel like we feel like we have to cover a lot of other things for linear regression. Sorry, I had to drink water. Because first of all, there are some questions that are actually very interesting in this book that they were attempting to answer. And I believe these questions are applicable, like very crucial for real world type of situations and problems that we have to answer as well. So, gosh, let me get my notes though. Okay. What is camera? Oh. Actually, I'm gonna restart my stream. One sec, guys. I'm sorry about that. Okay. Let's see here. So, all right. Welcome to this week's study group. Yesterday, um, I've actually could not make it on our usual day, but it's because I had to volunteer for my friend's work. He does this like it's pretty interesting. But anyways, yeah, let's move on. For this week, we are going to cover the rest of linear regression, and that we are actually going to cover like the last part of the chapter. And I think I'm going to discuss mostly about this because I don't believe we've been really that thorough from last week's lesson about linear regression. Well, granted, we did cover a lot, but there were some details, major details, that we did not cover that's actually very important. But most importantly, in this book, the ISLR book, there's these questions that are very intriguing and very important. That I think is very important because it actually applies to the real world, as opposed to making it conceptual. Like understanding statistical concepts or whatnot, but more as if it's asking like the more important questions that leads into a good algorithm or a good model in linear regression. And that is in 3.4, the marketing plan. And the marketing plan asks literally 7 major questions that actually makes up a very good model that it's asking. And these 7 generic questions can be applicable to the real world, and they're actually very essential for people who are analyzing data for the business, or for people that wants to learn, for education, and just plain reporting the advanced statistics, so that we can actually portray the knowledge to the real world. So the first question: is there a relationship between advertising sales and budget? So mind you, like last week we talked about sales data. The sales data consists of TV, radio, and newspaper, which is a multi-linear regression. If there is a linear relationship between what makes up the sales and which dependent variables are important or whatnot. And so on sales, onto TV, radio, newspaper, we talked about, is there going to be a relationship between advertising sales, which is the dependent variable, and budget? Which is just basically the independent variables. Budget meaning as if it's TV, radio, and newspaper. So we need to create a null hypothesis, the null hypothesis, and the alternative hypothesis. So for the null hypothesis, we have beta of TV equals radio equals newspaper, all equals 0. That means the null hypothesis means that there is actually no relationship between one another. There's no relationship between advertising sales and budget. Whereas the alternative hypothesis is that it is all those things, TV, radio, newspaper, greater or equal to 0. or greater than 0. I mean, not greater or equal, excuse me, greater than 0. So let me bust out my pen and paper. So let me show you guys. I'm so glad I bought this. I just bought this like 2 weeks ago, and I'm very happy with this purchase. Granted, my handwriting is a bit ghetto, but let's see here. Okay. So that's so ghetto. Is there a relationship between y and the x's? Y meaning that the dependent variable x is also the independent variable. So we need to create a hypothesis. The null hypothesis is that it's obviously you can see it from here. The null hypothesis is that there is no relationship between sales and budget, which basically is TV. Radio. I don't feel like writing the whole beta or what's it called? This variable that represents. I'm still writing it. And newspaper. God, can I spell? Equals 0, meaning that any of these relationships between y and the x's is 0. There is no relationship. Or h of a, which is the alternative hypothesis, is that TV equals radio equals newspaper is greater than 0. That means that, like, greater than 0 means that there at least has to be at least one of these independent variables have to have a relationship. At least one of these dependent variables have a relationship with the independent variable. So how can we do this? We calculate the Fstatistic. So in this Fstatistic, I forgot what it was though. Let's see here. On table 3.6, well, the Fstatistic, there is I'm following along with you guys, so I don't really know. Right. The Fstatistic is basically the total sum of squares minus the residual sum of squares divided by the number of predictors, which is basically the independent variables, all divided by residual sum of squares and n minus p minus 1 degrees of freedom times n minus p minus 1 degree of freedom. So n represents the number of data sets, p is the number of independent variables, and this one is actually an indicator of a degree of freedom. So when we're calculating this, we want to know if the linear regression setting is that when we have a multilinear regression, this Fstatistic actually matters. In the outcome, I don't know exactly the numbers, so I can't give you like a perfect example, But all you have to know is that once you calculate the total sum of squares minus the residual sum of squares of this, basically this thing, it's gonna have an outcome, whether if there is going to be a relationship, meaning the alternative hypothesis, it has to be larger than 1 to have any sort of relationship. And if there's no relationship, it's going to be closer to 1. So regardless, any answer, it's going to be more than 1. But how big of a 1 versus how small of, or how big of the answer versus how small of an answer really depends on the data that you actually have to really tell whether if there is going to be a relationship or not. So basically, if we follow the book right here, radio, TV, and newspaper, basically in this example, the Fstatistics is 570. So that's obviously way bigger than 1. And it basically provides evidence against the null hypothesis, you know. The large F statistic suggests that at least one of the advertised media must be related to sales. So, yeah. In this example, F equals 570 for, yeah, so radio, TV sales. Whoa, there's something that's flickering. That's crazy. Oh, that's insane. And basically what that entails is that if they have a larger than 1 and they have any sort of relationship, there's a 1. But what if F was like, what if F was like 100? Or not even 100, or 50, or 25, or 75, or 60, or even 3, or 1, 2. Or anything that's less than 570. What if it's smaller? So how do you tell whether if there actually is a relationship then, or whether if it's just basically noise? And so it basically it just basically questions that in this book. How large does the F statistic need to be before we can reject the null hypothesis and conclude that there is a relationship? So it turns out the answer depends on the values of n and p. So it really depends on the n and p. If n is large, basically if the number of data sets is large, then the F statistics, if it's even a little bit larger than 1, then you can conclude that there is an alternate. You can conclude that we have sufficient evidence to know that there is a relationship. we fail to reject the null hypothesis, basically, that there is no relationship. But if the n is small, though, it's the opposite. So you might have to have a bigger Fstatistic number, like just as big as 570 in this one, to actually conclude that there is sufficient evidence to support that there is a relationship, or there's clear evidence to support that we fail to we reject the null hypothesis. And so basically that's actually the first part. Now, regarding P, I mean, excuse me, not Q. Why am I saying Q for? Oh God, where am I? Okay. Sometimes we want to test that the particular subset of Q of the coefficients are 0. So basically, like, it's just basically N and P. I'm actually learning as I go here. I kind of forgot everything already. So we're testing that in the null hypothesis, all the coefficients are 0. Sometimes we want to test that particular subset of Q of the coefficient 0. This corresponds to the null hypothesis. Anyways, going back. Anyways, going back, that's basically step 1. You just basically calculate the Fstatistic. Fortunately for us, if we're going to do some programming, like using Python or R, you can summarize the algorithm that's already given to you using linear regression, and it already calculates the Fstatistic already. So you don't have to manually calculate this. This is all just like pen and paper. Just know that anything that is significantly larger than 1, there has to be some sort of relationship, and you can reject the null. So moving on, how strong is the relationship? This is where, how strong is the relationship then? This is where we actually delve into RSS, or RSE, or R squared. That's, oops. So there's actually 2 measures of models of accuracy. 1, 2, the R squared and the RSE. Residual squared error and R squared. Residual standard error and the R squared. So once we calculate that, if the RSE is 1681, RSE basically calculates the standard deviation away from the actual. In other words, it estimates the standard deviation of the response from the population regression line. And if the RSC equals 1,681, according to this example of the advertising and the sales data, if the mean value for the response is 14,000, we can conclude that there is a percentage error of 12%. Well, let me calculate if that's actually true. Oops, wrong way, wrong way. Yeah, exactly. So, first, what you need to do is that you need to find the mean value for the response, which is 14,000. Calculate that, and then divide, and then have this be divided by the mean value for the response. And there's a percentage error of 12%. So that's not too bad. I mean, so you just have to use some of your guesstimate. Whether if that's actually a strong relationship between the variable and the response. But for r squared, actually we just talked about RSC just now. It should be number 1. And my handwriting is asshole-ish. Anyways, r squared. R squared is just a percentage of variability in response that is explained by the predictors. So again, r squared has to be between 0 and 1. That's the result of an r squared has to be some sort of percentage. And so if you calculate the r squared, which you really don't once you're doing Python or R, it'll just say it. If it's bigger than 50, like, well, this is your judgment, but the rule of thumb is that if it's greater than 50%, then there is some sort of relationship, maybe. If it's greater than even more, like if it's like at least like 70%, then I'm pretty sure there is a strong relationship between that, the independent and dependent variable. Obviously, the opposite is true too. If it's less than 50%, you might have to say that there's a weak relationship between the variables and between the predictor and the outcome. You know what? I'm gonna have to have a standard terminology. I'm just gonna say independent, dependent variables for the sake of simplicity. Because last week we covered that there's so many different terminologies that mean the same thing. So I'm just gonna say independent, dependent for now on. If the dependent variable and the independent variable have a strong relationship, it's greater than 50. It's less than 50 if it's weak. That means it still has a relationship. It just has a weak relationship. So step 2 is like a gateway of finding which independent variables are necessary to use in a linear regression, so that you can actually have a strong predictor. Also, another reason is because you want to eliminate overfitting. If you actually put too many independent variables into a model, I mean, that's like prone to overfitting the model. You're probably only just going to make sense of what it looks like in the training data, but once you have a whole different data set, that might have an inaccurate response. So it might have too much variability in your model. Too much variance in your model. Which leads me on to the third question, which is which media which media contribute to the sales. So basically, which actually has a bigger significant impact to the dependent variable. I'm learning as I go here too, guys. Just letting you know. Oh, what did I write? Oh yeah, that's right. So this is really simple. If the p statistic is less than 0.05, there's like, you can tell that it contributes to the sales according to the each predictor's t statistics. If it's greater, obviously there's no significance at all whatsoever. In R, at least, there is a linear regression algorithm, and then if you do summary and then some sort of like variable that you've actually put in that predicted the linear regression, it'll list all the independent variables and their p-values. So it's really simple. Just so you know that there could be so many like different variables that actually do contribute, and you might. And that's something that's actually very interesting. Then we kind of have to question whether which ones are even more, which one can we iron out and which one can we iron in to create our model. Based upon our model. So how large is the effect of each medium on sales? That really brings on to that next question too. So how large is the effect? In ISLR, they actually do these things called confidence intervals. If there's 95% confidence intervals between TV, radio, and newspaper, you'll notice that for TV, there's a 0.043 to 0.049 confidence interval. So there's a positive impact on it. So is radio as well. But yeah, so is radio as well. But newspaper just doesn't seem like it because there's a negative in there and a 0. The reason why is because the confidence interval for TV and radio are narrow and far from 0. But the interval for the newspaper includes 0, indicating that the variable is not statistically significant given the values of TV and radio. Yep. So that's how you do it. You calculate the confidence intervals. Section 3.1.2 talks about how to calculate the confidence intervals, which I actually need to review because I honestly forgot. But just know that there is a confidence interval that you can judge to whether if you want to include which variables or which independent variables are should you include and which one should you just not include. Oh, right. But the caveat is that there's also there could be collinearity between even TV and radio, and we kind of have to question if collinearity is the reason that confidence intervals associated with newspaper is so wide. Excuse me. So we also need to calculate the VIF scores, which you don't actually have to calculate when you're programming it. It's just there is an algorithm, or there's a method for that in R and Python. You can so if the VIF score is 1.005, 1.145, and 1.145 for TV, radio, and newspaper, there could suggest no evidence of collinearity. So basically all you need to do is just know the confidence interval, and so calculate the know the confidence. Well, you don't even have to calculate. Just know the confidence CI. But question if there's any collinearity. Given if the CI is weak, given why the CI is weak for a certain independent variable. So going on to number 5. How accurate can accuracy? So how accurate can we predict the future sales? Now this is actually very crucial. Man, I have terrible handwriting. Sorry about that, guys. Also, I'm really not used to writing on a tablet. So, the accuracy. So, when we could already create a prediction using a method in Python or R, but the estimate depends on whether we wish to predict an individual response or the average response. If we are going to predict just an individual response, we use the prediction interval. If we want an average response for all the data sets, or all the values in the data set, we use a confidence interval. So, individual response, use prediction interval. I don't think this is useful anymore because my handwriting is so bad. I'm just gonna type it. That should be a better idea. Sorry, actually, my tablet backfired. I thought it was gonna be cool, but I guess not. So if you want to use an individual response, use prediction interval. If you want to know the average response, use confidence interval. And in R, at least there's an argument within one of the methods in R that you can switch between prediction and prediction interval and confidence interval. So that's actually really convenient to use. And the last thing you want to know is the relationship, and that's basically how we, before we go to number 6, prediction intervals will always be wider than confidence intervals because they account for the uncertainty associated with the irreducible error. So basically that's what it basically says right here. So if you want to do an individual response, you're never going to get an accurate answer compared as opposed to an average response, because the confidence interval will be too wide sometimes. So we're going to have to live with that. I mean, if the world gave us an actual predicted answer, we'd probably all die early and let the rich be super richer, you know? And let the poor be super poor. Because it's a dog-eat-dog world now, because it's all give us the answers for the next lottery ticket and the probability of that. Oh my god. Anyways, number 6, is the relationship linear? That's kind of an interesting question because we've always assumed that this was going to be linear, but maybe it might not be. In the whole advertising data set that we talked about, there actually wasn't, the data set actually wasn't linear. It actually have a curve, like a small curve, and then it goes up. Whereas if it was just a completely linear, then we could just use the linear regression, and then we'd be over with it, you know, using a good data set, and then using the correct algorithm. The residual plots, if the relationships are linear, if the relationship is linear, the residual plots should display no pattern. So let's see here. In the real world, there's I feel like there's really not that case, you know. But let's look at figure 3.5 for a sec, because that's what it shows. Where's figure 3.5? Ooh. Here we go. This thing right here. They're using sales, TV, and radio as predictors. From the pattern of the residuals, we see that there's a pronounced non-linear relationship in the data. See, it kind of curves. The positive residuals tend to lie along the 45-degree line, whereas all the negative residuals, they are basically split evenly. So they tend to lie away from the line, and the budgets are way more lopsided. So is it linear? Especially for this advertising data set? No. And this is no surprise, like in the real world data set, I don't think anything is going to be linear, really. But the reason why we're learning linear relationship, because it's a very important gateway to learn the concepts of other algorithms that are way more appropriate. But you really do need to understand your Fstatistics, your p-values, your confidence intervals, your your RSS and all that stuff. This is just an excuse to actually understand your foundational stuff for the next algorithm stuff. Anyways, is a relationship linear? No. All you need to do is just probably plot the lines and just basically see if it's linear or not. And we can actually see that once we're going to program later on. So the last question is there synergy among the advertising media? I kind of actually discussed this in Discord. I was a little confused at this part, but I think I get it now. Like, let's say radio and TV accounts for an effect, a relationship to the y variable, for the dependent variable, and if you have a 50% split even between sales and newspaper, that might contribute to the sales data way more than if it was just only TV or only newspaper. So in the book, it says the standard linear regression model assumes an additive relationship between the predictors and the response. An additive model is easier to interpret because the effect of each predictor on the responses unrelated to the values of the other predictors. However, the additive assumption may be unrealistic for certain data sets. Bingo! This is what you kind of have to watch out for, because we showed how there's an interaction term in the regression model. The interaction term is basically, you know what, I actually forgot. But it's basically, is there some sort of synergy effect that contributes, if there's parts of one variable and the next variable that actually contributes highly to the sales outcome or not. And this number 7 probably takes the most of understanding the statistics behind it, because there's a gigantic calculation to it. But basically what you can do is that if you finally find out there is a synergy between two independent variables, then you can actually do like that variable x that variable to actually create a new distinct variable, which is like a combination of the two variables, to contribute into the outcome, the dependent variable. So if there's levels of either TV or radio that are low, then the true sales are lower than predicted by the linear model. But when the advertising is split between the two media, then the model tends to underestimate the sales. So, and then it just goes on to it. You have to read 3.3.2. I have to do this myself. I'm not confident in teaching you that. But you notice how there's like a TV X radio, and that's a whole new thing that you can measure. And it's possible doing this in Python and R as well. But first you have to know if there is a relationship that like parts of TV and parts of radio has a more effect if you combine it into sales as opposed to only TV and only radio, you know. So yeah, that's actually basically the 7 questions that are very important. And let me read this a little bit. So an additive model is easy to interpret. The effect of each predictor on the response is unrelated to the values of the other predictors. Just know about that. However, the additive assumption may be unrealistic for certain data sets. In section 3.3.2, we showed how to include an interaction term in the regression model, and I gotta really review that part. A small p-value associated with the interaction term indicates the presence of such relationships. So figure 3.5 suggests that advertising data may not be additive. Including an interaction term in the model results in a substantial increase in R squared from around 90 to 97%. That's actually really good. Because really the whole goal is for us to have a strong relationship in R, to have a good prediction. All right. I think that's it for the day. I've actually spoke a little too long. Maybe I'm 10 minutes fast, but I think the 7 questions, you really have to like really know about this, um, because then if we move on to different like business questions or business questions, you really want to know, this is like the true backbone. You have to really question these 7 questions while you're evaluating and analyzing the linear regression model. Alright, well, thanks a lot, guys. I'll talk to you guys later.